Pose with the fans. Pose with the pose with the pose with the fans. Pose with the pose with the pose with the fans. Fans. Pose with the fans.
Hi guys, for this part I will explain to you the relationship between pressure, volume and temperature. For simple understanding, I will use ideal gas law, which is PV equal to nRT. For example, I will label this diagram into three parts, which is part A, part B and part C. For part A, I will turn off the hot plate and the temperature will remain constant, so that the pressure will remain constant also, followed by volume. For beaker B, I will increase the temperature by turn on the hot plate into medium level, so that the volume and pressure will follow using the formula PV equal to nRT. And then for beaker C, I will increase more the temperature by using high temperature for hot plate, so that when the temperature high, the pressure will be high also, then followed by the volume, so that we can know the relationship between pressure, volume and temperature.
Hi, so now I'm going to talk about how the PVT concept we learn in class are actually applied in real life lab work, specifically during our recent PVT lab visit. PVT stands for pressure, volume and temperature, and these three parameters are key to understanding how reservoir fluid behave under different conditions. Whether we are talking about oil, gas or condensate, their properties change as pressure and temperature change. This information is super important in petroleum engineering because it helps us estimate reserve, design production strategies and optimize recovery. But how do we actually get this data? That's where the lab comes in. During our PVT lab visit, we saw equipment like the PVT cell, mercury and piston pumps and setup for tests like constant composition, expansion and constant volume depletion. These tests allow us to measure important properties like the bubble point, gas oil ratio, formation volume factor and also viscosity. For example, in the constant volume depletion test, we observe how gas comes out of solution as pressure drops, exactly like we learn when studying the bubble point in class. We also learn how the formation volume factor change with the pressure, which is critical for converting reservoir volume to surface condition. So, visiting the lab helped me connect the dots between the PVT theory and how we actually measure and apply that data in the oil and gas industry. It's one thing to see in a textbook, but seeing it live really made me clear for the better understanding.
Hello, so me and my partner will be analyzing a PVT study for an oil sample from field A. So our task is to include in determining the saturation pressure, calculating compressibility and optimizing separator condition. So first, let's start with the saturation pressure. First, saturation pressure. Saturation pressure is a pressure at which gas begins to separate from the oil. It also known as bubble point pressure. To calculate it, we can use the pressure, volume, temperature data. The bubble point pressure is the point where the oil starts to form gas bubbles. We will calculate it manually by analyzing a PVT data from the field lab A and compare the result with our result using both correlation and Excel plugin. So after we got the calculation, we compare the calculated result and the graph readings in both pictures, confirm the calculation made using the Excel plugin and correlation. With the bubble point pressure, values from the plots being close to these numbers. Second, compressibility calculation. Next, we need to calculate the compressibility of the fluid, which tells us how much the fluid's volume changes with pressure. So we will use the formula of C is equal to delta V over V times delta P. We will calculate this below and above bubble point using both correlation and Excel plugin. And then we can compare the results from the report values. So the summary is, the compressibility values for both samples are consistent between the correlation method and Excel plugin method. That's showing is a very little variation.
Now, let us go ahead to calculating the optimum separator condition. We review the PVT report to find out the separator pressure and temperature that will provide maximum oil production and minimum gas loss. We have taken into two considerations, the solution gas oil ratio and the formation volume factor. Under ideal separator condition, we observed that RS and VO value were more efficient and stable. We use graphical analysis and report numerical value to determine the range of pressure and temperature that yield best separator performance. These are also crucial in delivering minimum shrinkage and best surface processing. Then, we quantified and graphed oil formation volume factor and solution gas oil ratio against the given pressure range, correcting them for the best separator condition. DO quantified the expansion of oil from the reservoir to surface condition. RS represent the volume of gas dissolved in the oil under different pressure. With the correlation and Excel add-ins, we plot PO versus pressure and RS versus pressure. We compare these two lab data to validate them. The curves were similar and any difference was likely to assumption in the correlation or small compositional difference in the fluid. To conclude, we already calculate the bubble point pressure from laboratory data and confirm it using correlation and plug-in utilities. Calculated compressibility above and below the bubble point. Identify the optimal separator condition to improve fluid processing. And the last one is calculating DO and RS trends with respect to pressure range using empirical and computational methods. This analysis helps in better understanding of reservoir fluid behavior, which is critical for successful oil recovery and production planning. Thank you for your time.
Hey everyone, so in this project, my partner and I worked on analyzing a PVT study for an oil sample from field A. Our main goals were to figure out the saturation pressure, calculate compressibility and optimize the separator conditions. First up, we look at the saturation pressure, which is the pressure at which gas starts separating from the oil, also known as bubble point pressure. We did some calculation with the PVT data and compared the results using both correlations and an Excel plugin. The cool thing is, the results lined up really well across all methods. Next, we calculated the compressibility of the fluid, which is basically how much the fluid's volume changes when pressure changes. We did this both above and below the bubble point, and again, the values were pretty consistent between the correlation methods and Excel plugin. Then we moved on to figuring out the best separator condition. We needed to find the pressure and temperature that would give us the most oil production and least amount of gas loss. By looking at things like gas oil ratio, RS, and formation volume factor, BO, we identified the best pressure and temperature ranges for the separator. We also graphed BO and RS against pressure and compared our results to lab data to make sure everything is checked out. Finally, to help explain how pressure, volume, temperature, PVT works, I used a simple example with ideal gas law, PVT and PV and RT. We saw how pressure, volume, and temperature are all connected and how this concept applies to understanding reservoir fluid behavior. To wrap it up, here's what we all did. First, we calculated the bubble point pressure and confirmed it using different methods. Then we calculated compressibility above and below bubble point. Next, we identified the optimal separator condition to improve fluid processing. And last but not least, we analyzed BO and RS trends to help optimize oil recovery. This project really helped me get a better grasp of how fluid behaviors affects oil production, which is super important in petroleum engineering. Thanks for watching. Bye!